Hello there, my name is Bartłomiej Nizio. I am a software engineer at Orbital, and today I would like to talk with you about building destruction on mobiles using Unity ECS. I will be talking a little bit about ECS, a little bit about building destruction, but I have decided not to use any code in the presentation since ECS code can be quite long and complex. So we'll focus mostly on the concepts. To give a little bit credibility to our work, I would like to introduce you to our studio, Orbital Night. We are a studio based in Poland. Our focus is mostly on hyper casuals and casuals on mobile devices. In recent years, we have specialized in making power fantasies and physics-driven games where core mechanics are constructed on physics behavior. Uh, Here are some of our hits. Maybe you are familiar with them, like Crazy Kick or Spire Blast. But let's go back to the topic of our presentation. And our goal is to create a building destruction suitable for castles. Castles are characterized with their brick layout. So we want every brick, every element to be reactive with the environment in this realistic and dynamic simulation. We want to maximize the number of dynamic elements on the scene, but at the same time, we want to achieve stable performance on mobiles. Let's hope for 60 FPS, which is a challenge on a mobile device. We also want to distinguish different materials like stone and wood, where stone is hardened and wood is easier to break. We also want to develop in Unity, since Unity is a go-to game engine to create games on mobile devices. So to achieve our goals, we need to find a suitable technology. In the past, we use a standard Unity approach with similar goals in our older game, Castle Wreck, but it turned out really well. But we wanted to have more stable performance and add more features. So we start to search for alternatives. And we decided to try out the ECS. So what we knew about entity component system is that it has advantage in processing many elements, which is what we were looking for with our simulation. And it has this kind of intuitive built-in multitasking, which would provide additional benefits in the simulation. Of course, ECS has some big disadvantages. First of all, it's in preview, so it might not work. It might have bugs. We didn't even know if it's possible to publish anything at the time. Of course, there are shortages in documentation. It also has a different production process, not something that we were used to with our templates and tools to develop and produce with standard Unity. So we have to be prepared that it could be more difficult to develop and distribute the game. So we have decided to try it out, make some tests, and see if it brings enough advantage to risk using it. So we made some tests. For example, as you can see in the presentation, there's a profiler screenshot of a simulation of 2,000 dynamic bodies that were activated at some point, and they just collapsed, and we collected data of how the simulation was computed. And as it turned out, although in both cases, ECS and the default Unity physics, FPS went to the roof. It achieved its minimal capacity on the phone, but ECS stabilized much faster, and in the end, it achieved higher FPS when stable. It is also not easy to make a physics test because rigid bodies they behave differently on each try. So we have to make an approximation of what actually is better. But ECS gives us enough confidence that it will be a better system for the simulation. So from the beginning, ECS gave us quite some trouble. It was just a different way to work, and not everything was implemented. For example, it was, I would say, impossible to work in the scene view at runtime because entities weren't reactive with the scene view. We couldn't edit anything in the scene view at runtime. And to collect and view data, there is this entity debugger view that it looks like a spreadsheet, and there you can find system and entities and their component and values. So it's just a little bit different to work with. We were also surprised with lack of physics in edit mode. We wanted to cast rays, detect colliders to establish joints between objects, but physics system, physics worlds were not active during edit mode. They're activated on runtime, and it was hard to make it work in edit mode because it required a custom bootstrapper to activate those, and it just took too much time to implement it. So we make a different approach. We converted all the ECS components, shapes, and physics bodies back to Unity equivalents, which are colliders and rigid bodies. Then make those rays with default Unity physics and establish joints, and then switch them back to ECS equivalents. It also turned out that joints are not breakable yet in ECS. So we needed to write our own systems to make them breakable. Also, writing code was a little bit challenging in ECS. For example, it was hard to measure performance. As you can see at the screenshot of a profiler, there is this system, a debug system that has the higher computation cost. And when we first saw it, we were surprised. What is this system? Maybe we should disable it. It's just so much, so very expensive. But it turned out that the system didn't do anything. It just finished all the jobs that were scheduled previously by the system. It has this job handle complete method, and this method took blame for the performance of the other systems. And the problem is that with multi-threading, multitasking, systems were delaying their performance cost. And it was hard to establish what is the actual cost of the performance. Additional thing was the huge cost of adding components to entities. We wanted to add components to act like flags to inform about the state of an entity. For example, if entity is dead, if entity is on fire, you could just add a component and change state. But the cost of this operation was very high because of how the ECS work. It has to change the chunk of an entity, which is like replacing it, it in a memory, and we're using command buffers to do that, but the cost was still very high. So we decided to use Boolean components and change the value instead of adding a component, and this bring a much lower cost for performance. And for ECS, it is just so much easier to make mistakes. You have to have a good knowledge about how to use native containers with proper jobs and systems. And we, for example, had a situation when we have this straightforward system where you just cast some rays to move the object accordingly. But because it was badly implemented, it took it ate up 20 FPS from the performance of a build. And those kind of mistakes happened all the time. And while we were learning and trying to develop at the same time. But at the end, we finally grasped how to use ECS, and from then everything started going much smoother. So let's dive into the implementation. The first thing we need to address was that individual rigid bodies were put together in a building would just collapse like a sandcastle. So we needed to make some connections to make the whole building whole. So we used joints to establish connections. We wanted to use the least amount of joints possible to achieve a greater performance. So at first we just connected every element with another with a single connection, and they would together create this straight line of connections. But when the building collapsed, it just looked like a spiral, and the effect was not really good. We tried with just vertical connections, but then again, the building would just collapse like a bunch of fries. So we needed to have two connections per object. So every object would have one horizontal and one vertical joint. So it gave us four connections per object. And this kind of configuration gave us an effect of a cement. However, the building with this configuration of joints was very wobbly. It behaved like a jelly when you pushed it or make an explosion. It was too dynamic, and we need to make something more rigid to behave more like a stone tower. So we came up with wall joints. Wall joints are basically joints that connect a body with the wall. In Unity, it is implemented as a joint is connected with nothing. And we put a couple of those joints inside the tower, and it gave this robust effect that the tower was not wobbly anymore. And if we increase the number of wall joints, the tower would become much harder to destroy. With less joints, it was less stable and could even collapse on itself. So we have to find the perfect equilibrium of wall joints to achieve the results we are looking for. As you can see in the picture, yellow lines represent horizontal and vertical joints, while the blue dots are the wall joints in the building. As I previously mentioned, we wanted to implement different materials and to simulate their property differently. We added multipliers for their explosion forces. So when the explosion will occur, the wooden elements would gain higher velocity than stones and would break the wooden structure much easier. And also we added different break forces based on materials. So when the building collapsed on itself, it would collapse much easier with, for example, wooden material than the stone one. But of course, the hardest part of this project was not creating a realistic building simulation. It was to achieve performance on mobile devices. And what we find out in ECS was that we can create colliders without callbacks, without collision events, which saved us a lot of overhead. Of course, this solution has its drawback. We couldn't process those collisions and react to them, but we found different alternatives to achieve similar results. We used segments to collect the collision data and leave individual bricks with no callbacks and high performance. And because in the end, what was the most important is to reduce the number of active bodies in the scene. Because we wanted to have bigger structures, bigger castles, more towers and walls. And if all objects were active at the same time, the performance would drop to zero. So we need a way to know which objects to awake and which to disable from the simulation at the time. And our solution to this was to divide buildings into segments. Each building was segmented into this vertical and horizontal modules that were connected horizontally and vertically. So when we activated element, an object inside a segment, the whole segment would activate so that the whole tower could collapse. Also, when the lower segment was activated, the higher segment was activated also. The same goes with the with side segments, so the horizontal segments. And each segment had its own collider trigger that would collect the collision queries of the debris of objects that would fly in the air and hit the building. And because individual bricks hadn't had no callbacks, those triggers of a segment would collect collision data and activate the whole segment instead, which save us a lot of performance. But building segments were not enough because at some point we needed to deactivate the single bricks to allow other segments to be activated. So when the bricks move, we didn't know exactly in which segments to activate, and we created this other set of segments, Rubble segments, that were placed evenly on the scene with their own individual triggers, and they would accumulate those objects that were no longer part of the building. And for example, if some rubble would land on another building and we would hit the base of this building would collapse. We needed to activate not only elements of this building, but also all the rubble that was on it. And because we could detect the trigger of the rubble segment, we could also activate those elements and they would fall with the building. Lastly, it all went out to how many objects are active on the scene. So we needed to find a solution to reduce the number of elements. And our solution was to use composite objects. For example, you can see in the picture this cross element. It uses 4 bricks instead of 1 and 2 colliders instead of 4. So we achieve 4 times less calculation on a brick and 2 times less calculation on the collision of the colliders. And this kind of layout of elements were bringing also a little bit realism to the distraction, because not every object needed to be detached from the other to create realistic visual feedback. And here you can see the outcome. There are a couple of pictures I taken from the simulation. It was hard to show the effects without a movie clip, but I hope it is sufficient to show the results. At the final note, I would like to say that I think that ECS worked very well in this situation. It gave us quite some trouble, but I would happily use it again in another project that would require such a performance. So thank you very much. This is the end of the presentation. If you have any question, please ask them now or write me an email. Thank you.